Hi, it's time for another math easy solution. To discuss further into hyperbolic functions and look at the catenary again and basically derive that same formula that I did in my earlier video, but now using an alternative method. I'll call that method number 2, which is pretty interesting. So let's just follow along this one. So recall from method 1 is just the original derivation video of the catenary. You can see that in my earlier video in the description. We'll have the link here to the video. So recall from that video that we first set up the xy axis such that the lowest point of the catenary crosses the y-axis, i.e. it is the y-intercept at that lowest point, and then we basically drew a free body diagram from the lowest point to an arbitrary point extended from it. Yeah, so let's just follow that same step as in that video. So let's say we have a x, y axis like this, y, x, but in this case I'll just draw a arbitrary curve that is in fact a asymmetric catenary. Doesn't matter where it is. Let's just draw something like this, and now the lowest point is here and it crosses the y axis. So now that we have this section, what we'll do is now start from the lowest point, then go to an arbitrary point, let's say somewhere around here, take this segment across like this, and then basically drag it in here and remove it and blow it up and basically draw a free body diagram like this, where this point is the lowest point. It has a horizontal tension. When you remove that, we'll call that T0, and then this extends like that curve all the way up to here, and then this has a point or a tension that is tangent to this. We'll call this T, and that is this tangent line across there like that. Yeah, so this force is tangent to the curve. Yeah, so then what we'll write is this length of this segment, we'll call this length S, and now this has a linear weight density, call it W naught of this segment or wire. Let's say it has a uniform linear density per unit length like that, and this one we'll call it a W naught, just like in my earlier video, and I'll write that here. And I'll write this as weight per unit length like that, so it's a linear weight density of that. So yeah, to get the entire weight or force, you just multiply this uniform one by this length across, and then if we draw this at the center of gravity, and I'll go over free body diagrams when I go over my physics tutorials later on in my video series, so stay tuned for those. But here's a quick refresher if you haven't already. So then we'll draw a downwards force like this. This is due to the weight of gravity based on this linear weight density, and now this is going to be just this W naught times it by the length of that cable S. And now what I'll do is I'll just move this right here, and now for this one we need to draw the horizontal and vertical components of this tension across there. And this one, if we call this theta like that, this has a horizontal component like this one using trigonometry. This force right here, this is going to be T cosine theta, because T is the hypotenuse there, and then the vertical side like that is going to be T sine theta. And then as in the method 1, we use equilibrium, so the sum of the forces in the horizontal direction x has to equal to 0, so it's not moving. So then what we end up having is the horizontal one will have TO equals to the horizontal component of this tension. That's only horizontal force besides this one there, so we'll have TO equals to T cosine theta like that. And now similarly, the sum of the forces in the y direction equals to 0 in the vertical ones, so that's going to be, well, the vertical component there, and then this one right here due to the weight. So we'll have this one as, and I'll write this as W naught times S equals to T sine theta. So yeah, now that we have these, what I'm going to do now is I'm going to divide this or this one by it like that. I'll actually write that other way around. So we're going to divide sine by the cosine term there. So what we'll have is T sine, and I'll do that right here, put this arrow across, t sine theta over t cosine theta equals to now this this w naught times s divided by t 0. Yeah, so what we end up having here is, well, this t's cancel, so then we'll have a sine over a cosine. That's just by definition tan theta. And also as in method 1, so I'll write as in method 1, what we did was we let these two terms combine them into one. So what I'll do is I'll let a equals to TO over W right there. So this is going to be right here is 1 over A. So what we end up having is, we'll put this all the way down here. So we have S over A equals to tan theta. In other words, we can move the S across. So what we have is S, the length of the segment, is equal to A tan theta, like that. Yeah, so now this theta, what we're going to do is, well, that is at this tangent line, like that. So what we can do as well, we could write this out, and I'll write note at the tangent, at the tangent to that point, or the tangent at the end of the line segment. What we end up having is, I'll have x, y. This is, for example, if we have a point like this, this right here is extends like that, and what I'll do is, this is that tension t, but I'll remove this and just draw this as a tangent line across, pretend it's infinitely small. So what we have is, over at this horizontal one, this could be our dx, the horizontal distance. This is going to be our dy at infinitely small. This is our ds, or that incrementally small length of the line there. And again, our theta is that same one as above. So what we end up having here is tan theta equals to opposite over adjacent, dy over dx. And then what we also have is sine theta is equal to opposite over hypotenuse. So we have dy over ds. And then the cosine theta is equal to dx over ds. So these will be all pretty useful, and I'll move this over here and circle this or box it in because we will be using these. So now is where we get to our method 2, and this one I actually got from Wikipedia, and it was pretty useful still. It's actually a pretty interesting derivation. So what we'll do is, well, first another note that, well, x, this is just a function. If you look at x, it includes, or basically depends on s. It's a line segment there. Tan, the derivative is dependent on x there. So then x is a function of s, but s is also a function of the angle right here. As that angle changes, the length of that segment will be different because this is going to be at a different point. So this is what we end up having is x is a function of s and a function of s. So this is why we could apply chain rule. So what we can do, or what what Wikipedia does, is it does dx over d theta. So the way it does this using chain rule as well, we could go ds over, dx. First of all, what we could do using chain rule, we could take the derivative in terms of ds, because it's a function of it, and then multiply this out by the function or the derivative inside over here, ds over d theta. And I'll write this out as chain rule. And you can learn more in my earlier videos on that. So now that we've written it like this, notice dx over ds, that is just cosine like that. So that equals to cosine theta. And now the derivative ds over d theta, that's a derivative right here. So what we could do is write this as, I'll take the a out, just a constant, d of tan theta over d theta, like that. And now if you recall from my earlier video, the derivative of tan is just going to be secant squared. So then this equals to cosine theta times it by secant squared theta. And I forgot to put that a there, that constant a. Now this one here, secant, remember, is just equal to, well, let's write this down, a cosine theta, and then that's the same thing as 1 over cosine squared theta. So like that. That's just by definition. So what we can do is cancel this, and then this equals to a over cosine theta. And again, by definition, 1 over cosine theta is just equal to secant theta, like that. So this is what our dx over d theta is equal to. Now the next step that Wikipedia does is it does the same for dx over dy over d theta. And again, same thing as above. You have theta, y, and s all in the same function. So this again means that we're going to have y is a function of s, which s is also a function of theta, like that. This is all interconnected like that. And again, using chain rule, the derivative here is, we could just write this as dy over ds, and then times it by the derivative of ds over d theta. And now we can go scroll above for dy over ds. That is right here, that's sine theta. So this equals to sine theta, and then multiply by this ds over d theta. We already know that. That is just this. That's this one, derivative of tan theta, or a tan theta. So we could put the a in front here and just write this as secant squared theta. But again, this is going to be equal to, just to simplify it further, a sine theta times it by 1 over cosine squared theta. Or we could break this up into cosine theta and then put another cosine theta here. So the same thing as 1 over cosine squared theta. So that we get, so then what we get here is a tan. Yeah, so we get a tan theta. This equals to a tan theta, and then this just goes up back to a secant theta, like that. And this is our equal to our dy over d theta, like that. Circle this. Yeah, so now what we could do, or the next step that Wikipedia does, is it takes these and then uses or solves the integral of it to get x and y. So this formula, write this as 1, this one as 2. So what we could do is use that one formula right here and then just move the d theta on the other side, so we get a dx equals to a secant theta and then d theta, so that we could take the integral. Yeah, now recall the integral of this. What we end up getting is, well, we get x, and then as I showed in my earlier video, I should take the constant out, and then the integral of secant is going to be ln of absolute value of secant theta. Now you can see the proof of this in my earlier video, and I'll put that also in the description below. Then absolute value, then plus tan theta, like that, plus a constant, c1. Now since we have an absolute value here, but recall that this angle we have, it actually is going to be between 0 and pi over 2, or 90 degrees. So we have, I'll write this down, I'll just write it over here. Since our angle is, or in our derivation is going to be, angle is going to be less than pi over 2, so it's not going to be perfectly vertical, and then let's just go greater than 0. Yeah, so that we actually have a line segment S. So we have this one right here, and recall that the curve of, yeah, I'll move that over there. So recall that the curve of tangent, so the xy, the tangent looks something like this, and it keeps repeating itself onwards and fro, and this is where at between here is at pi over 2, and we'll write this as theta, like that. Just put x there, so that this is tan theta, and this is always positive between here. I'll just put a arrow like that. And also for cosine, it's going to look something like this, actually. Yeah, it's going to look something like that. Starts off at 1, then just goes upwards, and there's the same, it has the same intercept like that, and then it just keeps repeating itself like this as well. And this is for cosine theta, and you can see my earlier videos on tan, cosine, and sine, and I graphed those. And as you see here, this is all positive, and it just keeps repeating itself. But between 0 and 2, no, at 0 and pi over 2, this is all positive there, so we can just remove that absolute value sign. So thus x equals to a ln of just regular bracket secant theta plus tan theta, and then plus a constant c1. And now what we could do is, well, similarly for the for the y, well, that's equation 2 right there, a tan secant theta. So what we'll do is, I'll write this as number 2 formula above, but then move that d theta across. We'll have a dy equals to an a tan theta secant theta d theta, and then take the integral of both sides. And now also, my earlier video I showed that this tan theta secant theta is actually just the antiderivative. Actually, never mind, it's the derivative of the antiderivative, and I'll take the constant out, a secant theta, like that. Yeah, in other words, if you take the derivative of secant theta, what we'll get is tan theta secant theta, and then if you take again the integral of this, you get back to here, and again plus constant c2. And you can see that in my earlier video as well. Take the derivative of secant theta, you'll get that. And this is right here is y. Yeah, so now what we have is these constants c1 and c2, but to simplify it, what I'll do is, well, for the y one, I'm going to do is let c2 just equals to constant c, just so it's like my earlier videos. And then what we end up having is y is equal to a secant theta plus c, like that, just for simplification. We could even make it equal to 0 if we want to, but I'll just keep it like that. And now for this one here, I'm going to actually make that one go to 0, and I'm going to shift the x-axis. Actually, it's not the x-axis. I'm going to shift the y-axis so that c1 equals to 0. In fact, we could do that for both, and the reason is, well, just look at how this x is equal to. So if we had an arbitrary point across here, this is going to be y. Yeah, this is going to be y like that. This is our x, and let's say we had a point across here, and the distance from here to here, this x position right here, yeah, is such that we have a constant c1 right here. And then we also have in between here and here is well, this one right here, a ln secant theta tan theta. So this part right here, this difference is, and I'll just write this down like this. This entire difference is a ln secant theta plus tan theta. And that's all the way for this point x and y. But then we could just shift the y-axis. If we shifted it right here, so move this over here, so that we end up having is like this, and I'll cut this over. So I'll just erase this one right there, make it a bit neater, move this over, and just put an arrow like this. Just draw a better arrow like that. So we shift this y all the way across here, and then draw it in dashed lines across, meaning that we're just shifting it across, and I'll call this y like that, or y2. So we shifted just exactly on the c1. So now we're dealing with a distance from here to here, which is just this a ln secant theta plus tan theta. Let's put this in regular brackets like that. So again, we shift that so that eventually, yeah, we'll just have the lowest point. It's going to all intersect. The lowest point is going to be at the y-intercept, and c1 is equal to 0, like that. Yeah, so thus we have y equals a secant theta plus c, just use that constant c, and now this x, we get rid of that one. What we end up having is, so we'll write thus x equals to a ln secant theta plus tan theta, like that. And now this is where the Wikipedia page, what it does is it starts making more sense of how we're going to write it as a catenary function, as in my earlier method 1 video. So what I'll do now is take both of these as powers of e, like that. Or actually, before I do that, I'm going to move this a onto this side. So what we end up having is a x over a equals to a ln secant theta plus tan theta, like that, and then take it e to the both sides, so we could cancel these lns out. So what we end up having is an e to the x over a equals to those ones just cancel, so this is just going to equal to secant theta plus tan theta, like that. And now that we have an e to the x over a, what we could also do is take the reciprocal or the negative power, so we could go e to the negative x over a. This just equals to, well, this whole thing, secant theta plus tan theta to the power of negative 1. In other words, this equals to, I'll write it down actually over here, equals to 1 over secant theta plus tan theta. This is a very abstract derivation video, but it's just, I find it really interesting nonetheless. So we have this 1 over secant theta plus tan theta, but now what we could do is multiply this by the negative, I think it's called negative reciprocal or something like that. The top and bottom, I'm going to multiply this by secant minus tan theta, so we can cancel the middle term out. Now we have secant theta minus tan theta. So again, nothing changes. This is just timesing it by 1. So we could multiply this inside, and then this one at the top is going to be secant theta minus tan theta, like that, over, now secant times secant is going to be secant squared theta. Now secant times tan theta, that's going to be tan theta secant theta. And then this one times that one, that's going to be a plus tan theta secant theta. So those just cancel. I'll just erase those. That's why we multiply by the negative. And now finally tan theta, and then times it by negative, this one right here, tan squared theta. Yeah, so that's what we have there. But also now recall the trig identity. So recall what we have is just a generic one, sine squared theta plus cosine squared theta equals to 1. Now if you divide by both sides by cosine squared, what we end up getting is cosine squared theta over cosine squared theta. This becomes tan squared theta plus, now we have this one just cancels, equals to 1. This one now is secant squared theta. So now if we move this over to this side, what we end up getting is a secant squared minus tan squared theta equals to 1. And I'll just put an arrow across there. This part here equals to 1. So what we end up having is this entire one just equals that. So thus we have e to the negative x over a equals to just secant theta minus tan theta. And also what we have is from the earlier one, and e to the x over a, as is shown above. I'll move this over like this and scroll to that one. That's just secant theta plus tan theta. So that just equals to secant theta plus tan theta. So now notice what we have right here. So if we add these up, if we add e to the x over a plus e to the negative x over a, now we can cancel these tan theta. So what we end up having is a secant theta, and then these just cancel. So I'll just write this down: secant theta plus tan theta, and then plus secant theta minus tan theta, like that. These cancel, these add up. So what we get is 2 secant theta. And notice this, we could divide the 2 out there, and then what we end up getting is a secant theta equals to an e to the x over a plus e to the negative x over a over 2. And as I showed in my earlier video, well, this is just by definition. This is just a hyperbolic cosine of x over a, or cosh x over a. So that's that's the part where I find it's really fascinating. I had to do this video, and then going back up to our y function, y equals to a cosh x over a plus c. That's secant theta. That's amazing. Yeah, so that is our answer right there. So thus, y equals to a secant theta plus c. In other words, that equals to cosh x over a. So y equals to a cosh x over a plus c, and there is the catenary, like that. Amazing. But we're not done yet. It's actually quite fascinating like that, doing it all this random stuff to get to it. But we're not done yet, because if we subtract instead of divide there, or I mean instead of add, what we get is also, let's write also, if we have e to the x over a minus e to the negative x over a, this equals to, scrolling up again, we have a secant theta plus tan theta, so secant theta plus tan theta. Now we have a minus, and then the top part is secant theta minus tan theta. So we have a secant theta minus tan theta. Now notice what happens is secants cancel, and then we have this is going to be negative plus tan theta. Those add up. This equals to 2 tan theta. Divide the 2 out on this side. Again, now what we end up having is a tan theta equals to e to the x minus x over a minus e to the negative x over a. This divides it out by 2, and this is again by definition, that's hyperbolic sine or sinh x over a, and that is absolutely amazing. But now notice where we have this tan theta. Scroll up, that is the length of that segment S. So scroll up, this is far ways. Where is that S1? Should be somewhere there. There it is. S, the length of that segment, equals to a tan theta. So what we get is, scroll away, so thus S equals to a tan, alright, a tan theta equals to a sinh x over a, like that. Absolutely amazing, like this. And this is the length of the line segment or cable from the starting point, or cable. Amazing. And I'll just write that out, hashtag amazing. So we get both the length and the equation of the catenary all in one go, and all this abstract way using the chain rule and random differentiation and integration and trigonometry, hyperbolic trig. Very amazing. It was all for today. Hopefully you enjoyed and followed along. It's very extensive. It starts making sense later on in this video, but very amazing proof. Anyways, that's all for today. Thanks for watching. Like always, you can download these exact notes in the link below, as well as viewing these as Steemit. All the notes will be there. Follow me at MES, and also make sure to check out my math forums and start posting whatever cool math or science related stuff you find. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.